This program is brought to you by Stanford University. Please visit us at stanford.edu.
We're going to plunge deeply into the Hamiltonian method of mechanics, not quantum mechanics. We've studied the Lagrangian method. We've studied the principle of least action. We've even gone to the extremely advanced study of Newton's equations. Tonight is Hamilton's night. Part of the point, in fact, maybe the main point of the Hamiltonian formulation of mechanics goes back to something that I talked about at the very first lecture. We talked about the basic structure of classical thinking, classical mechanics, but not classical mechanics quite, but something even a little more primitive. We talked about discrete systems, the coin, which could either be heads, no, this way is heads or tails. And that's a two-state system, two simple states. And then we talked about possible laws of evolution. One simple law of evolution is nothing happens. Evolution now might mean a sequence of states separated by a small time interval, or discrete time interval, a tenth of a second, or whatever. We update every tenth of a second. Then we spoke about a simple law of nature, which was a simple law of coin flipping, or coin changing, which would be no change at all. It's here, and it's here, and it's here, without doing anything. That's a simple law of evolution. Another less simple law of evolution is if it's heads, then the next time it's tails. If it's tails, the next time it's heads. Tails, heads, tails, heads, tails, heads. Both of these rules have the feature that if you know the state of the system at any instant of time, you know it at the next instant of time. In other words, the updating rule is precise. But also, the backdating rule is also precise. If you know where you are at any instant, you know where you were. We even talked about the general structure of such simple theories. Instead of just two states, we could imagine a system with many states, each one being represented by a point in a space. We might as well now call that space phase space. It's the phase space of a simple discrete system. In this case, it's got 1, 2, 3, 4, 5, 6. If I stop there with only 6 states, then we could be talking about a die. A die isn't dice. 6 possible configurations. Add 2 more. I don't know. We could be talking. What system has 8 states?
3 pennies.
3 coins. 3 coins. Precisely. So this is a general kind of situation, and the basic setup, in fact, the definition of a phase space is if you know where you are in the phase space, you know where you'll be next, and you know where you came from. So there's a rule which could be represented simply by a set of arrows which tells you where to go next. Nope, you can't come back because you've already been there. Here, 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 and then back to here. For example, you can have other kinds of laws, not different in kind, but different in detail. For example, you could have some closed loops like this. So, wherever you are, you go to the next place, but now there's some closed sort of cycles, so that if you're on this cycle, you will stay there, and if you're on this cycle, you will stay there. This corresponds to the existence of a conservation law. We can imagine that these 3 states over here are labeled as having property equal to +1, and over here, property, the same property, is -1. Well, if you've got +1, you stay +1. +1 never becomes -1, and -1 never becomes +1, because all of the configurations with number -1 go to configurations with number -1, and so forth. But both of these kinds of laws have the property that if you know where you are, you know where you'll be, and you know where you were. That's to be contrasted with a law which might look something like this. If you're over here, you go to here. If you're over here, you go to here. And if you're over here, you go to here. That's a very definite updating rule. Wherever you are, you know where to go next. But there's something funny about it. Namely, in particular, you can't go backward in a unique way. You can go backward from this point. From this point, you know that you must have come from here. But if you're over here, you don't know whether you came from here or whether you came from here. What's going on here is points are running into each other. There's yet another way to think of it. Imagine the phase space being populated with points, and the point, in fact, let's imagine the entire phase space is populated with red dots. And the red dots all move. They do a dance. The dance is simply to follow the trajectories as they're prescribed by the law, whatever the law is. So this red dot goes to here, this red dot goes to here, this red dot goes to here, this red dot goes to here. Notice every red dot knows where to go, knows where to come from. And there's a kind of rigidity to the red dots. None disappear, none spontaneously appear, none disappear, none appear. They simply just rigidly, or what's an even better word than rigidly? A fluid, incompressible, a kind of incompressible motion where points don't run into each other. Same thing here. Same thing here. If we populate the points with red dots and we allow them to move along the arrows, instant by instant by instant, each instant the number of red dots is the same. They don't run into each other. They don't bifurcate. The whole thing just moves in an incompressible way. On the other hand, with this law, we could start a red point at each place, but then after one motion, this one would have disappeared, never to reappear, and we would have only two places which were occupied, going back and forth, back and forth. There would be some loss, in a sense, of points in the phase space. Phase space points would not be conserved. The whole point of Hamilton's mechanics, Hamilton's form of mechanics, is number one, it's a form in which every point knows where to go next and knows where it came from without points ever being lost or gained. In other words, a kind of rigid motion in a phase space, or an incompressible motion of the points in phase space, which may also be called information conservation. We'll see, we'll talk about that a little bit further in the future. Okay, another point of Hamilton's equations, let's think about ordinary F equals ma type equations. They're not of this form. Why not? Well, let's suppose you know where you are. Let's make a plot. Here's the positions of a particle, possible positions of a particle. Here's the particle x, y, and z. Supposing I know the particle is over here. Do I know where it will be next? No. I need to know something else. I need to know not only where it is now, but I need to know where it was an instant back. In other words, I need to know the position and the velocity. Knowing the position and the velocity is the same thing as knowing the position at an instant and knowing the position a slight bit earlier. So I need two pieces of information. I need to know where the object is, and I also need a kind of ghost piece of information, which is where it was an instant ago. And that's enough to tell me where it will be next. Next means after a short prescribed period of time. So specifying the locations of a system, by now we can simply call them the cues of a system, does not constitute a phase space. The phase space constitutes everything you need to know in order to tell where you'll be next, but in such a way that there's a rigidity to the motion. A rigidity to the motion, points never gained nor lost. That's what phase space is. Phase space is a way of representing the configurations of a mechanical system so that the motions are described much as I've described these discrete motions. We'll come back to it in detail.
May I ask a question here before
Yeah.
we move on?
Yeah.
And I wonder if you can talk about what some of the insights or pressures or motivations were for this reformulation of Newtonian mechanics.
Well,
were there problems?
yeah, I think the Lagrangian formulation was formulated by people for practical reasons. The practical reasons being most systems were awfully complicated and difficult to apply F equals ma. And so a more general formulation, which was not dependent on particular sets of coordinates. In many, many contexts, rectilinear coordinates are simply not appropriate to a problem. Components of vectors are not appropriate to a problem or not particularly useful. Motion, for example, motion of a particle on the flat blackboard can be nicely described by x's and y's, and we can use x and y components and write F equals ma. Motion on the surface of a sphere, an object moving around on the surface of a sphere, it's not natural in any special sense to introduce rectangular coordinates. You can't introduce rectangular coordinates onto the sphere. You can introduce coordinates, latitude and longitude, but you can't introduce rectangular coordinates. And the naive idea of components, rectangular Cartesian coordinates is not useful. So it's useful to define mechanics in a way that doesn't depend on any specific set of coordinates. That was Lagrange's motivation. What Hamilton was smoking, I don't know. But what he developed was an extremely beautiful, elegant formulation of mechanics, which I don't think he ever really used for anything. He simply admired it, and physicists admired it afterwards. It turned out to be very useful. Part of the usefulness of it was because it does conserve information in the same sense that I've described over here. I'm sure he was aware of that, but I don't know if it was foremost in his mind. But ultimately, the real power of it came when quantum mechanics was developed. So it's hard for me to put myself in Hamilton's position. I mean, it was one of these brilliant mathematical insights that kind of came from nowhere. Just somehow he saw the structures there in ways that I think most of us would not have. And so no, I can't really give you his intuitions. What we can do is do it. And after we've done it, go out back and talk about why it's so useful and why it's of such power. I'm not particularly sure that anybody realized how powerful and useful it was until quantum mechanics was developed. I think that really was the time when people first really began feeling they had to learn what Hamilton had to say. Of course, he was long dead by that time. All right, another observation about it is it takes a certain number of second-order differential equations. F equals ma is a second-order differential equation for each component. Second order means that it involves second derivatives. Not first derivatives, but second derivatives. So it may also involve a first derivative here and there, but it contains second derivatives. It contains accelerations, second derivatives with respect to time of something. How many equations are there? Well, if there are a certain number of particles in a certain number of dimensions, that tells you how many equations there are. One particle, there are 3 equations. 2 particles, there are 6 equations, and so forth, each one being a second-order differential equation. What Hamilton's equations are in general, you can always take a system of second-order differential equations, let's say n of them, and replace them by twice as many first-order equations that only contain first derivatives. It's very easy. It's so easy it's almost stupid. So let's discuss how you take n second-order equations. The method is completely general, but I'll just illustrate it for Newton's equations. Supposing we have a certain number of equations of the form derivative, second derivative of some ith component of x by dt squared is equal to the ith component of force divided by the mass. I've written acceleration is equal to f over m. I don't know why exactly. I just wanted to write the acceleration on the left-hand side. Let's suppose now that there are n such differential equations. Let's take that and make 2n equations, each of which only contains a first-time derivative. To do that, first of all, define. Now, we can do it many ways, but I'm going to do it in a particular way that'll be in order to get familiar with terminology. First of all, let's define the xi by dt, and let's throw in a factor of the mass. The mass of the ith, that's one mass. Everybody has the same mass. Let's take m times the x sub I dt and give it a name. What do we call it? We call it p sub I. Now, let's write, I don't know why I put m on the left-hand, on the right-hand side of the equation. Why did I do that? Let's put it back where it belongs. F equals ma. Now let's write f equals ma in the form.
Mi?
Let's just make one m. All right, now let's take, this is of course a first order equation. It only contains first time derivatives. But now let's write f equals ma in the form dp by dt is equal to f I. Both of these equations are only first-order equations, but there are twice as many of them. There are twice as many equations, but each one only containing first-time derivatives. They become a system of 2n differential equations, but twice as many variables. And now, what are the twice as many variables? X sub I and p sub I. First order equations are the kind which tell you where to go if you know where you are without knowing where you were. A first order equation tells you how to update to the next position if you know where you are. But knowing where you are now means knowing where you are in the phase space. It's equivalent to the old view. You again need to know two things, a position and something equivalent to a velocity. But it's just a different mindset. Thinking about the phase space gives you a picture, x and p, in which wherever you are, you know where to go next. So there's no new physics in it, no new laws of nature, just a different mindset, thinking about the state of a system not as a configuration, but as a combination of a position and a momentum. Or not just one position and momentum, but a position and a momentum for each degree of freedom, for each coordinate. More generally, of course, we would talk about Q's and P's, or Q's and pi's. I think I'm going to give up the notation pi. I got that, we'll just call canonical momenta P's and be done with it. But those are the various motivations, various properties of the Hamiltonian description. It's the equation of, the Hamiltonian description of mechanics is the equations for how things move around on a phase space. Knowing where you are, they tell you where you move next. In fact, you can almost think of it just as, did I erase what I had to? Yeah, I did erase what we had, but let's put it back. We thought of a law as being a kind of flow. A flow of the points in phase space. We're going to see that there's a natural sense in which mechanics constitutes a flow in the phase space. Wherever you are, you know where to go next. And if you were to imagine populating the phase space, populating the phase space would mean taking a lot of identical systems and starting each one at a different point in the phase space and watching them as they evolve. That would define a flow in this phase space. And it's that flow in the phase space that Hamiltonian mechanics is all about. It's almost as if the points in phase space were a kind of fluid, and we're studying how that fluid moves. If we're interested in any specific system, then we think of it as a little particle moving along with the flow. We start at some place, we allow it to move along with the flow, and follow its coordinates and its momentum. All right, now we need a small piece of mathematics. It's an easy piece of mathematics, but it's a rather formal piece. It's the mathematics that's called the Legendre transformation. I'm going to do it first in the simplest possible case. Suppose there are two variables. Let me call them V and P. Just secretly, between you and me, V stands for velocity and P stands for momentum. But now forget I told you that, because we're going to think about the Legendre transformation as a mathematical trick in many, many different contexts. All right, so there are two variables. And let's suppose, whoops, it's a funny P, isn't it? V and P. But they're not independent variables. In fact, there's really only one variable. They're functions of each other. They're functions of each other, and for simplicity, not for simplicity, this is important. Let's suppose they're single-valued functions of each other. Single-valued function means that if you know P, you know V, and if you know V, you know P. No ambiguity. That means the graph of P versus V looks something like that. What it can't do is it's not allowed to do that. Why not? Because if it did this, there would be certain values of P where you would have an ambiguity about what V is. It's also not allowed to do this, because then there would be certain values of V where you wouldn't know what P was. Single valued means that the graph of the function P versus V looks like this. Any point on it, or for any value of V, there's a unique P, and for any value of P, there's a unique V. Actually, just for simplicity, although this is not important, let's just draw the graph so that it goes to the origin. then if we have such a single-valued function, not just a single-valued function, but a one-to-one function, meaning it's single-valued whether you think about it as p as a function of v or v as a function of p, then it's possible to invent a pair of functions, one which I'll call L, secretly the Lagrangian. And the Lagrangian is a function of v. And it has the property that the derivative of the Lagrangian with respect to v defines p. Why would I bother inventing a function L whose derivative with respect to v is p? Well, we'll come to why, but I can always do it. This is just ordinary derivative for the moment. Since there's only one variable v, we don't have to make it a partial derivative. d L by dv. We're going to find that given L, we can construct a symmetrically related function that we're going to call h. H is to be regarded as a function of p. When we think about L, we will think about v as the independent variable. When we think about h, we will think about p as the independent variable. Of course, L is also a function of p because v is a function of p. Of course, h is also a function of v because p is a function of v. So, but each one is thought of as a function of its own variable, L of v or h of p. And the relationship is h and L are connected by the derivative of h with respect to p is v. This is a completely symmetrical relation between p and v and between L and h. The derivative with respect to v of L is p. The derivative of p of h is v. Now, let me show you why that's always possible to do, and to show you the relationship between L and h. Okay, let's take our function, which for simplicity I just had passed through the origin, but you can work it out whether it passes through the origin or not. Notice the derivative of L with respect to v is equal to p. Think of that as p as a function of v, of course. V is the independent variable in the top equation. So p is really a function of v, as it is over here, p of v. Remember, the p is a function of v. I've just rewrote it over here. P of v. We can also think of v as a function of p. And now, let's solve this equation for L by just writing that L is equal to the integral of p of v dv. Does everybody recognize that? If the derivative of L is p, then L is the integral of p. We can write this as d. Does everybody recognize what I've done here?
Is that a definite, indefinite?
Okay, that can be taken to be a definite integral, and for definiteness, let's take it to be the integral from 0. But it doesn't matter. It doesn't matter where we take the integral from, but let's, for definiteness, take it from 0, from v equals 0. If we differentiate an integral, we just get the integrand. So if we differentiate L with respect to, let's put v up here, definite integral from 0 to v, p of v dv. If you differentiate an integral with respect to the endpoint of integration, you just get the integrand. So that's this relationship here. Derivative of L is equal to p. We can always do this. Here, that's L of the endpoint, if you like. All right, we can now draw a picture of what L means, at least on this graph. L is the area, L of V, or let's say L of V is constructed in the following way. You go to your point V, you draw that line, and then you consider all the area underneath the curve here. This is not a triangle, it's a curve. That's the integral of P of V dV, and it's L at point V. L of V. It has the property that if you differentiate it with respect to V, you get P. Now, what about H? Well, we can do the same thing with H. H must be the integral of V dt, just by symmetry. The other equation is that H of P is the integral, we can again start at 0 and go to P, of V of P dP. Notice that if we differentiate H with respect to P, we just get V. That's the other defining equation here. The derivative of H with respect to P is equal to V. All right, so the geometry of that then is that H, the area in here is H of P, and the area in here is L of V. This area in here is the integral of V of P dP. Does that need further explanation? Well, now we know the relationship between H and L. Take H and add it to L. H plus L is the area of this whole rectangle. What's the area of the rectangle? It's P times V. This is usually written as H is equal to PV minus L. But it's clearly the same thing. For some reason, we tend to think of L first and then try to figure out what H is. All right, so now let's write our system of equations that are called a Legendre transformation. You start with an L of V. You differentiate L of V, ordinary derivative we'll do here. Derivative of L with respect to V defines P, then gives you P as a function of V. Then you construct H by multiplying P times V and subtracting L. Now L, of course, is a function of V, but wherever you see V, substitute its value in terms of P. So we can think of this as L, same script around here, L of V, but V is a function of P. So, and V is also a function of P here. So H gets to be thought of as a function of P. L is a function of V. And when we do this, I'll now prove, although it's clear from the geometry here, that the derivative of H with respect to P is V. Let's do the little manipulation algebraically. Here's what we do. We consider a small change of P and ask how much H changes. How much does H change when we change P? Let's work it out. The change in H, let's just call it delta H, small change in H, is first of all, what's the change in a product? If we change If we make a small change in the values of some variables, what's the change in a product?
Sum of two terms.
The sum of two terms, one term being the first factor times the change in the second, and vice versa. All right, so first of all, we get a term which is P times the small change in V. The second term is V plus the small change in P. And finally, minus the derivative of a Lagrangian, the derivative of L with respect to V. Remember that L depends only on V, times the change in V. Well, wait a minute. I defined the L by dV to be called P. That was the way that I constructed P from L. The L by dV is equal to P. So look right here, we have the L by dV. I'm sorry I sometimes write partial derivatives and sometimes total. It doesn't matter. There's only one variable. Partial and total are the same. All right, so this thing is P. Well, here I have P dV. Here I have minus P dV. So these two cancel completely. These two are the same, and therefore cancel. Well, not the same, but opposite. And that just leaves the change in H is V times the change in P. That's the same thing as saying that the H by dP is equal to V. The H by dP is equal to V. In other words, the change in H, when I change P a little bit, is just equal to V. Okay, that is the Legendre transformation. So L, define the L dV to be P, then construct H, which is PV minus L, and now you have a reciprocal relationship where the H by dP is equal to V. So if we interchange L and we interchange L and H, and we also interchange P and V, it's completely symmetric. They're completely symmetrically related to each other. This little demonstration over here is nothing but the geometry of that rectangle being divided into H and L. That's a mathematical construction which is not only, which is at the heart of many, many things, in particular mechanics, but also thermodynamics. Thermodynamics is just filled with Legendre transformations all over the place, and variables are related in pairs, Legendre pairs. Now what happens if there are many V's? Instead of just one V, supposing there are many of them, then the definitions go as follows. The derivative of L with respect to the IV is the IP. Now just keep, you should probably remember what V is. V is some velocity, and in Lagrangian mechanics, keep in mind that the derivative of a Lagrangian with respect to a velocity is a momentum. This is just, all right, let's apply this to Lagrangian mechanics in a few minutes. But this is not a new relationship for us. Now, of course, we should use partial derivatives because I'm imagining many variables. Partial of L with respect to V sub I. That's P sub I. Definition at this point. Okay. Now we construct H of P. Not of a single momentum, but of a collection of P's. H of P means H of all of the P's. And this becomes summation over all of the I's, P sub I, V sub I, minus L. This may start to look familiar to you. Let's go through the same little derivation here. Now, the change in h is a sum of terms of p sub I, v sub I. I'm not going to write summation signs. Whenever I write a p sub I and a v sub I like that and so forth, think sum over the i's. All right, so first of all, a p sub I delta v sub I, a v sub I delta p sub I, and then a derivative of L with respect to v sub I times delta v sub I. When I change things a little bit, this is what happens to h. Again, exactly the same pattern. The L by dv sub I is the same as p sub I. So they cancel. The things inside rate cancel. And all I'm left with is that the change in h is equal to the ith v variable times the change in the ith p variable. From this, you could easily read off that the derivative of h, the partial derivative of h, with respect to p sub I is equal to v sub I. In other words, the change in h, if you only change one of the p's, let's say the third p, the change in h, if you change p sub 3 a little bit, is just v sub 3, keeping all the other p's fixed. So the derivative of h with respect to p sub I is just v sub I. Okay, so again, same kind of reciprocity. The L by dv sub I is p sub I. The h by dp sub I is v sub I. Completely symmetrically related to each other. Now at the moment, these are just abstract variables. Sometimes I've called one of them a momentum. Sometimes I've called one of them a velocity. But they could be just abstract variables. And as I said, there are many applications of the change of variables from a v-type variable to a p-type variable that's kept track of by what I've usually called generating functions, L and H. All right, but our interest is in mechanics. In mechanics, the Lagrangian is not only a function of velocities, it's also a function of positions. We haven't talked about positions at all. We have velocities here, things I call v, and we have things I call p. The relationship between p's and v's and Lagrangians and Hamiltonians is exactly what I've written, but with the coordinates q, just going along for the ride. Just going along as if you didn't care about them, as if they were just passive. So let me show you how the relationship between Hamiltonians and Lagrangians is nothing but a Legendre transformation of exactly this type, with the extra added ingredient that there's some more variables that go along for the ride. All right, now we're doing mechanics. We have a Lagrangian. The Lagrangian is a function of what? It's a function of the q dots. But let's call the q dots v's, velocities, generalized velocities, v sub I. Q sub I dot is by definition v sub I. So then the Lagrangian is a function of the v's and the q's. Don't confuse q's with p's. V sub I is equal to q dot. Let me write up here another equation of mechanics that you're familiar with. P sub I is the derivative of the Lagrangian with respect to q dot. Remember that? The L by dq dot defines P. But that's the same as saying dL by dV. dL by dV equals P sub I. That's the first of our equations over here. So we start to see the Legendre transformation between p's and velocities beginning to shape up. And it's simply the definition of canonical momentum as the derivative of Lagrangian with respect to q dot. Next, let's define the Hamiltonian. I'm absolutely repeating myself now, but I'm repeating myself in the language of mechanics. Let's define the Hamiltonian H to be the sum of P sub I what? P sub I V sub I. Usually we write P sub I Q sub I dot, right? That's the language that we've done previously. But Q sub I dot is nothing but V sub I. So let's put V sub I. Minus Lagrangian. That's precisely the same definition that we had for the Hamiltonian, I think, in the last two lectures. So we see the pattern shaping up. But now let's calculate the small change in H when we change things. What things? We're going to change the P's and the Q's. What happens if we make small changes in P's and Q's? How does the Hamiltonian change? Let's calculate that.
You're taking the velocity to be a function of P and Q.
It is a
When
function
you did the
of P and
Legendre
Q.
transformation.
Generally, that's right. In general, you can think of Q as just going along as for a ride as a set of parameters.
Okay.
Right.
But the velocity depends on,
But yeah, that's
especially
right.
P.
The whole thing, yeah, that's right. So that's correct. Now, okay, what was said was correct. Let me not rephrase it, but let me just restate it. Now, the relationship between the P's and the V's is such that P is a function not just of V, but also the Q's. And V is a function of the P's and the Q's. But you can simply think of the Q's as being parameters at this point, which, as I said, go along for the ride for the moment. The point is, of course, when you calculate dl by dv sub I, in general, it might contain some Q dependence and not just V dependence. But that's okay. Just pursue it. Okay, let's calculate the change in H when you change things a little bit. Change things means change everything a little bit, P's and Q's. All right, the change in H. Same thing as before. Is first of all the sum, which I won't write the summation sign, P sub I delta V sub I plus V sub I delta P sub I. And now we have minus the derivative of the Lagrangian. There are two things that the Lagrangian depends on. Let's see which way I wrote. dl by dq sub I delta q sub I and minus dl by the v sub I delta v sub I. Lagrangians depend on q's and v's, and now we're varying everything in sight, p's and q's. You don't have to separately vary the velocities, because you know the velocities if you know the p's and q's. Okay. So there we are. That's the formula for changing h a little bit. It has several terms, p sub I delta v sub I, v sub I delta p sub I. Derivative of Lagrangian with respect to q has a change in q. Derivative of Lagrangian with respect to v delta v. Okay, it's a little bit complicated, but fortunately big pieces of it just cancel, just as they did over here. In fact, the same rate cancellation takes place over here. Remember that the L by dv sub I is p sub I. Here's p sub I. Here's p sub I. Things in the red squares cancel again. They're gone. The other two terms can't cancel each other. One involves delta p, the other involves delta q. Those are independent variations. They can't cancel each other. But what we can write down now is that the derivative of the Hamiltonian with respect to p sub I, that's a small change in h when you change p sub I a little bit, keeping q sub I fixed, the h by the p sub I, keeping the q's fixed, is just what? What do you read off this? V sub I, and the h by the q sub I, what's that? What's this? It's minus dl by dq sub I. Now so far, okay, that's not bad. Some nice equations, but they get a little bit nicer. dl by dv sub I, right? Well, no, sorry, dl by dq sub I, right? That's it. You remember the Lagrange's equations? dl by dq sub I, what's that? Okay, let's write down Lagrange's equations over here. d by dt of dl by dq sub I dot is equal to dl by dq sub I. That's Lagrange's equations. What's dl by dq dot? P. So this is, the left-hand side is p dot I is equal to dl by dq sub I. That's all it says. That the time derivative of the canonical momentum is dl by dq. Well, let's look at what we have here. We have dl by dq, right? That's just equal to minus p dot. That's Lagrange's equations. P dot is dl by dq. So we have one equation. Let's get rid of the middleman here. We don't need him. The h by dq is minus the time derivative of p. But what is vi? Q dot. I'm going to go through this again. I'm going to do it again. Oh, these, of course, are Hamilton's equations. They're quite beautiful. H is a function of p's and q's. That's the way you think about it. The Hamiltonian is a function of p's and q's, momenta and coordinates. You get rid of the velocities. Replace them by p's. And then the derivative of the Hamiltonian with respect to p's defines the q dots, and the derivative of the Hamiltonian with respect to q's is minus the p dots. That's the structure of mechanics in the Hamiltonian nutshell, if you like. Let's go through it again, just since it was a series of steps, all of which are abstract, none of which are highly intuitive. Let's go through it again. Here we have h is equal to summation p sub I, v sub I, minus L. L being a function of q and v. Now let's make a little variation. That's going to be equal p sub I delta v sub I plus v sub I delta p sub I minus the change in the Lagrangian. What's that? Oh, sorry, excuse me, thank you. Minus v sub I delta p sub I. But now we have to calculate the change in L. The change in L is minus the derivative of L with respect to whatever it depends on. But it depends on Q's, delta Q's, and it depends on V's. Everybody gets an I. should be a summation sign, which I'm too lazy to write. Okay, now, first of all, what cancels? The things multiplying delta V cancel. Why? Here you have p sub I, and here, sorry, did I say that right? Yes? Yeah. Yeah. The L by d v sub I, that's p sub I. Definition of p sub I. The L by d v sub I. That's how we define canonical momentum. Gone, gone. And then we look at what's left over, and we see that the derivative of h with respect to p sub I is v sub I, but v sub I is q dot. And then we look at the other one that says the derivative of h with respect to q sub I is equal to minus the L by dq sub I, minus, but then we use Lagrange's equations. The L by dq sub I is d by dt of p sub I, that's Lagrange's equation, or just minus p dot. So we see that mechanics, in great generality, gets repackaged as a system of first-order equations of very great simplicity. You need to know one function of p's and q's. Knowing that function of p's and q's immediately by differentiation tells you how the point moves through phase space. It tells you the velocity through phase space. Q dot, of course, is just the ordinary velocity, but the combination q dot and p dot, let's put the sign on the other side over here. The combination q dot and p dot is a kind of velocity through the phase space. It tells you, if you know p and q, you plug it in to h, calculate the h dp, the h dq. If you know p and q, then you immediately know p dot and q dot. So it reduces mechanics to a system of first-order equations for p's and q's. Every p has a partner called q, every q has a partner called p. They come in pairs, and the Hamilton equations are two for each I. A pair of equations for each I. Let's do it, just for simplicity, for f equals ma. Let's just check that it really is correct. For f equals ma, as I said, I have no idea what motivated Hamilton to write these things down, but they certainly do have a very, very simple structure. And one of the things they show you is that, surprisingly, with very, very different physical interpretation, p's and q's seem to be very, very different things. Q's are coordinates, p's are velocities, are connected to velocities, and yet there's this enormous symmetry between p's and q's. They seem to come into the equations in an extremely parallel and symmetric way, apart from a single minus sign over here. They seem to enter in a symmetric way into mechanics. And it's the study of these equations which really defines modern mechanics, if you like, modern classical mechanics. Let's draw a picture to indicate what's going on. Here's general phase space, P and Q. It's not just one variable, there's many variables. Some subset are called P's, half of them are called P's, half of them are called Q's. I can't draw them all on the blackboard, so I'll draw just one P and one Q. At every point, where's my equations? Here they are. At every point, I could calculate the h by dp and the h by dq and tell you exactly what q dot and p dot are. That defines a kind of velocity vector through the phase space. Not an ordinary velocity, but a phase space velocity. Let's draw that phase space velocity as an arrow. It's showing which way that point is moving in the phase space. And the length of the arrow we can take to represent how fast you're moving through the phase space. And so what the Hamiltonian gives you is a kind of flow through the phase space where the arrows are long, you're moving fast, where the arrows are small, you move slowly. And the velocity, as I said, is related to derivatives. Notice one funny thing, that the q velocity is a p derivative, and the p velocity is minus a q derivative. Okay? So it's not that q dot is the derivative of h with respect to q, and p dot is the derivative of h with respect to p. They get crossed here. They get crossed in the equations. That has a profound implication, as we'll see in a moment. Any questions about Hamilton's equations up to now?
Any second order system?
Any second order system can always be, just by defining the first derivatives to be new variables, then that simply defines a set of twice as many first order equations. That's trivial. But this elegant structure here is far more than that. It has some properties that we'll see in a moment. Yeah.
Are there any systems where P and B are not one-to-one relationships?
When it happens, they're usually badly defined systems for which the evolution is not well defined and usually rejected as being. You mean, are there any systems in nature which require? No.
Things with circular systems with friction, doesn't that be slowly?
Well, first of all, friction is outside the boundaries of Lagrangian and Hamiltonian mechanics.
Okay.
Now, not really, because all systems in nature are of this type, and friction is a part of nature, but as I emphasized over and over again, you don't really see friction in a system unless you ignore a large number of coordinates. Friction is simply the excitation and the moving around of microscopic coordinates that you don't keep track of. So, yeah, let me see, I'm trying to think, are there any systems that I can think of where you can't invert the relation between coordinates and momenta? Yeah, I can think of one. No, I can't think of any. No, I'm sorry, I was going to say something. No, I can't think of any offhand that make physical sense. We'll talk about why, and we'll talk about the importance of this one-to-one soon enough.
How about the falling at terminal velocity?
No, that's friction. That's friction. What's happening is right. You cannot write equations with friction in this form. Friction outside the boundaries of this formulation. In the sense that if you wrote the equations that you normally write down for friction, they won't be of this form. If you write the equations governing all of the molecules, every single one of them, and keep track of them all, then there's simply a huge number of equations which do have this form. So introducing friction is a way of approximating a very, very large number of equations of this form by a very small number of equations and ignoring the motion of most of the degrees of freedom. Energy is leaking off into other degrees of freedom. Okay. So friction we don't want to deal with now. No. Friction is exceedingly complicated.
if we define H as that lower left-hand corner,
Yes.
and then take delta H,
Yes.
and we apply the Euler-Lagrange equations, then we get Hamilton's equation.
That's
right?
correct.
Okay. Now, but where is this Legendre thing coming in here? I mean,
Well, here, we did dl by dv is p, and dh by d. Here, this is the Legendre transformation.
what is is it the equation? Is it the right-hand side? Is it
It's taking a function of v. What is it? It's a procedure. It's a procedure of changing variables, if you like. Changing variables from a set called v to a set called p.
Is there any way you could describe that in words? I mean, I can sort of follow the arithmetic here, the algebra.
The Legendre transformation is a whole bunch of arithmetic that goes into it.
Well, you can go from X to U or, anything like that.
If you like, to me, this is the clearest definition of what you're doing. You have a pair of variables, v and p. They're connected to each other. If they're connected in a one-to-one way, then you can define an L of v and an h of p. L of v is the integral under this curve out to some v. H of p is the integral over this curve up to p. The derivative of L with respect to v is p, and the derivative of h with respect to p is v. P times v is L plus h. That's the simple geometry of it. Why is it so useful? You get used to it, and you do it over and over again, and you begin to see why it's useful. But I would suggest we just go with it, and we will find out just how useful Hamilton's equations are. Yeah.
So you require that function to be single valued, right?
Which one?
What happens?
Yeah.
What happens if it's not single valued?
Then you have a bad system. Then you have a system which physics, well, it usually means the equations of motion break down at some point, some breakdown in the predictivity of the equations, some singularity happens.
Sure. Can you identify a physical situation that would represent that?
Sure, no.
Oh, okay.
We could write down some Lagrangians and Hamiltonians which are bad and try to see why they're bad. I think that's a good thing to do. I'm not going to do it tonight. Somebody send me an email. Just send me an email saying write down some bad systems, and we'll write down some examples where things don't work out well and try to follow them and see where the motion breaks down. See what happens to the motion, how it tells you all of a sudden you don't know which way to go. It usually means at some point the equation of motion simply is singular. There's some infinity in it, and something breaks down that doesn't tell you where to go. Something in the equation becomes infinite as a general rule.
Well, presumably it means that your physics is wrong at some point.
I think it usually always means your physics is wrong.
Yeah.
Yeah. I know at least one example where it means something can travel with infinite velocity. All kinds of things can go wrong. But I think it's a good idea to take an example or two where you cannot invert the relationship between velocity and momentum and see exactly what goes wrong. And I will do that for you. But, if you send me an email message, we can do it.
Kind of a strange question. Why is it okay to have an infinite number of degrees of freedom in quantum mechanics when we're frightened of many degrees of freedom in friction?
No, it's not. Well, first of all, we can have an infinite number of degrees of freedom in classical mechanics. Infinite doesn't have to do with the difference between quantum mechanics and classical mechanics. A field has an infinite number of degrees of freedom. Right? Are we frightened of it? It can get pretty frightening. Having a field can lead to friction, for example. An electron accelerating radiates. It radiates photons. The radiation of those photons tend to act like a kind of friction. And it can get very, very complicated to follow the motion of an electron, including radiation reaction and so forth. Why are we afraid? We're not afraid of the many degrees of freedom. We just have to remember that they're there. I think you're asking me why it's so terribly difficult to derive the laws of friction and the laws of mechanics. Well, that is hard. But it's also hard to derive the laws of radiation reaction. It is hard to derive the laws of friction. But that's not for tonight in any case. For tonight, we want to discuss energy conservation, among other things. We already discussed energy conservation several times, but it's interesting to see how these equations, from the present perspective, these now become the equations of mechanics. This is a new formulation of mechanics based on h of p and q. Given an h of p and q, we now have a phase space. You have a motion through the phase space. You can imagine dots in the phase space, a fluid of points in the phase space, moving each point with a velocity that depends on its position according to these equations. And so it's a flow of a fluid. And it's simply a new way of formulating mechanics. Let's forget about all the old ways. Oh, I said I would work it out for you for the ordinary particle. Let's do that first. Ordinary particle, again, 1/2 mg squared minus u of x. That's the Lagrangian. 1/2 mx dot squared. Now I've replaced q by x. We've done this before, haven't we? What is it that I want to do? I just want to check these equations. Okay. So what is a Hamiltonian? We've done that before. Everybody remember that it's p squared over 2m plus u of x? P squared over 2m plus u of x is the Hamiltonian. Let's just check Hamilton's equations. The h by dp, differentiate that, that's p over m. That's what it is. Is p over m equal to q dot? Or in other words, is it equal to x dot? Yes, it is. And x dot is equal to p. So the first of Hamilton's equations, the h by dp is equal to q dot. That's nothing but the definition of momentum in terms of velocity. And what about the other equation? The h by dx minus the h by dx should equal p dot. The h by dx, that's just du by dx, minus du by dx, that's equal to p dot. Well, that's just Newton's equations. Mass times acceleration is equal to force. So the second equation, typically the way it works, is the first equation is the relationship between velocity and momentum. Okay? It's just p over m equals x dot in the simple case here. It's the second equation which really looks more like F equals ma. This is mass times acceleration, and this is force. Okay, so it does work. It is correct. It is true. And it is equivalent to all the other formulations. We could work out some more complicated examples, and maybe we will. But first, let's concentrate on, in this new form, let's concentrate on energy conservation. Let's see if we can prove directly that energy is conserved. Let's calculate the h dt. Time derivative of the Hamiltonian. If the Hamiltonian is energy, which it is, then it should be conserved. Its time derivative should be 0. Let's calculate it. It's equal to the derivative of h with respect to p times p dot plus the derivative of h with respect to q times q dot. Summed over I. The change in h when you change p times p dot plus the change in h when you change q times q dot. That's the change in the Hamiltonian per unit time. But now let's use Hamilton's equations for p dot and q dot. What is p dot? P dot, this is equal to sum I, dh by dp sub I. That's this. But what is p sub I dot? Can somebody read it to me? It's just a sign that I don't remember. Minus. That's minus. So minus dh by dq, right? And how about this one? This is plus dh by dq dh by dp sub I. And they cancel. That's what the minus sign is doing there.
Is that equation if and only if, so if we have the conservation of energy, we get Hamilton's equations?
I think it's possible to imagine equations which have a conservation of energy which are not of the Hamilton form. If you have Hamilton's equations, with a time-independent Hamiltonian, I've assumed there's no explicit dependence on the Hamiltonian on time. Then you do get energy conservation. The other way, no. I think you can certainly have equations which have conservation laws, conservation of an energy, without them being of Hamilton's form. So it's not if and only if. All right, so we see that these two terms simply cancel each other. And energy conservation is a very, very simple consequence of Hamilton's equations. It's kind of interesting. What this says is that if you take a point and you follow it, now from now on I want you to think about this phase space as a collection of points that you can follow in time. As you follow them in time, you stay on a contour of constant energy. Imagine this phase space, and imagine it being filled with contours of energy. In other words, surfaces on which the energy is constant. It's simply filled up with surfaces on which the energy is constant. The phase point, meaning a point in this phase space as you follow it, stays on the same surface of constant energy. That's just energy conservation. And the fluid flows, the fluid defined by the phase space dust, think of it, dust in phase space, flows along these lines, which are lines of constant energy. The lines of constant energy, in general, could be closed. They don't have to look like this. They could be closed curves. For example, we studied a case last time called the harmonic oscillator, in which h was proportional to p squared plus x squared. Well, let's forget the constants. It was just forgetting the constants. It was essentially p squared plus x squared. So in that case, the contours of constant energy were just circles around the origin. The contours can be open or off to infinity. They can be closed curves. They can even be a dot. That corresponds to a motion which doesn't go anywhere, it just sits there. For example, the harmonic oscillator, which has neither position, which is at the origin with no velocity. It simply sits there, it doesn't move. That's a kind of degenerate circle right at the origin. So the phase point moves on these surfaces. This is very much like the discrete situation where you have different closed pieces of the phase space, and that defines a conservation law. Which one of the cycles you're on? We'll call those cycles. Well, in phase space, it's very similar. Every point is on some contour of constant energy, and you move along those contours. Yeah.
The density of points is constant, right? Because
We're gonna talk about that. Yeah.
if the density of points is constant, how do you get these diverging lines?
Oh, well, that's easy, actually. We haven't discussed the fact yet that the density of points is constant. But let me answer your question. Okay, so let's imagine lines that look like this. So the fluid comes in and goes through a narrow channel. What happens when fluid goes through a narrow channel? It moves faster. It moves faster just so that the density doesn't change. A big lump of fluid comes in and it doesn't want to change its volume, so it has to squeeze between these lines faster. The lesson is where the lines clump up and get close, where the contours get close, the fluid is moving fast. That's, in fact, what Hamilton's equations say. When the contours are close together, think about a contour map. What does it mean on a contour map that the contours are very close? Steep. It's steep, right? It means the altitude is changing very fast. What does it mean on the contours of constant energy that the contours are very close together? It means that H is changing rapidly with respect to either P or Q or some combination of P and Q. So, where the lines clump up is where the H by dP and the H by dQ is large, and it's where the fluid is moving fast. Okay. So the lines can diverge all right. It's just that the places where they diverge like that, the fluid slows down. And we're gonna study that behavior a little bit.
Can you have closed curves and open ones in the same?
What's that?
Can you have closed curves together with open ones?
Absolutely. Let me give you an example. The pendulum. In the pendulum, small oscillations at the bottom are closed curves. The system just goes back and forth, just cycles over the same defined closed curves. When it swings over the top like this, they sort of correspond to open curves. Well, let me give you, let's sit it there. Forget the pendulum. Take a particle that's moving on a washboard potential like that. A potential which is just a sine wave. All right. If you start down near the bottom here and you give the particle a little bit of energy, all it does is oscillate back and forth. So it looks like the harmonic oscillator. In fact, it is a harmonic oscillator plus a little bit of extra. All right, so it just oscillates back and forth, and the contours are closed curves. So for small energy, the contours are closed curves. Give it a big energy, and it just goes whistling off over the top of the washboard. If it has enough energy to climb over the top and keep going, then the curves are open. The system doesn't come back to itself, it just keeps going off forever and ever. So yes, you can certainly have both closed and open curves in the same phase space. Be interesting to try to, I'm not going to do it, but it'll be interesting to try to plot what the contours of constant energy look like here on the phase space. Any other questions? Is there anything you want me to go back over? Yes.
generalized coordinate, is pi always a constant multiple of qi prime?
Say it again.
Qi dot.
Wait, say it again extremely clearly.
In generalized coordinates.
Generalized coordinate.
Yeah, is pi always a constant multiple of qi dot?
Nope. Definitely not. It can, no, not at all. No, it's just, we can invent all sorts of Hamiltonians. Here's a Hamiltonian. H is equal, instead of p squared plus q squared, let's take p cubed plus x cubed instead of p squared plus x squared. This doesn't correspond to any system that I know about in nature, but there's nothing wrong with it from the point of view of the Hamiltonian. Now, what are the equations? The equations are that derivative of h with respect to p is equal to x dot, and that's 3p squared is equal to x dot. Well, that does not say that the relation between p and x dot is that p is a constant multiple of x dot. So the answer is no, not in general. This is sort of unusual, but you could have an x here. That would be less unusual. No, sorry, x times p squared. Also, x times p occurs in Hamiltonians, but x times p squared. Then you would have the h by dp is x times p, and you would have p and x, the relationship between them having an extra factor of x. So no. There's no reason for such a simple relationship. Yeah.
It sounds like we're describing sort of a perpetual motion of sorts.
Really?
Would that be an accurate statement?
No. Well, yeah. Motion is perpetual. Motion is perpetual. That's why energy is conserved. But I'm not sure what you're getting at.
The idea that when you factor in friction, that you're actually transferring the energy into another part of the...
Yeah, okay. Before we can address the real meaning of perpetual motion and the pros and cons of it and so forth, we have to understand something about thermodynamics, and we have to understand the difference between usable and non-usable energy and entropy and all that sort of stuff. So we're now at a more basic level studying the individual degrees of freedom of a system. Microscope, for example, if it's this table with all the molecules moving around in it and so forth, or the air in the room, these are the equations that really do govern the entire system. In various kinds of approximations, you divide energy into usable energy or available energy and unavailable energy. Heat is unavailable energy, but that's got to do with the second law of thermodynamics, which we haven't got to yet. I would hope to get to it. It would be nice to be able to get to it. It's deeply connected with these equations, and it's deeply connected with the structure of motion and phase space, but we're not there yet. Before we understand that thermodynamics, we have to understand chaos, and we are not ready to do that tonight. Hopefully we'll get to it. Maybe. Okay, so let's discuss other conservation laws. Energy is a conservation law that follows just from Hamilton's equations here. There are other conservation laws, but let's look at the general form of them. We know from the Lagrangian point of view that conservation laws have to do with symmetries. I'm going to suppress that now. Later on we'll come back to it and discuss symmetries from the Hamiltonian point of view, but now let's not worry about why there might be a conservation law. Just let's see what it means to have a conservation law. What the necessary and sufficient conditions for a conservation law. Let's ask whether the quantity A is conserved or not. What does A A is a function of the phase space. Wherever you are in the phase space, A has some value. It's a function of the P's and the Q's, or equivalently a function of position and velocity. Let me give you an example. We worked out a number of times ago that the angular momentum of a particle moving in a plane is given by x times py minus y times px. It's a function of the p's and the q's. In general, all quantities that we might be interested in are functions of positions and momenta. If we know the position and momentum of something, we know everything about it. So in particular, we know the value of its various quantities. Let's ask whether A of P and Q might be conserved. Might it be conserved? And under what conditions would it be conserved? What mathematical conditions? Now I want to express those conditions in terms of Hamilton's equations. That's going to introduce for us a new set of quantities called Poisson brackets, fish brackets, for those who don't speak French. Okay, this is easy. All we want to know is whether the time derivative of A is 0 or not. In fact, let's just calculate the time derivative of A. dA by dt. Let's just do it. Brute force will calculate it. It's the derivative of A with respect to P sub I times P sub I dot plus the derivative of A with respect to Q sub I times Q sub I dot. I'm going to write the summation sign explicitly now for a little while. Summation over I. But now let's substitute in for P sub I dot and Q sub I dot their value in terms of the Hamiltonian. So this is sum on I, derivative of A with respect to P sub I. What's P sub I dot? Again, sign. I can never remember the sign. It's minus, right? Minus dH by dQ sub I. So we have dA by dP sub I, dH by dQ sub I. Now what's this one? This is plus dA by dQ sub I, and Q dot, that's dH dP, right? Well, look at that. That's kind of interesting. We find out that the time derivative of any quantity is given by the sum of two terms. Let me start with this one. dA by dQ, dH by dP. So if you know what A is, and you also know what the Hamiltonian is, you can compute these things. dA by dQ, dH by dP, minus dA by dP, dH by dQ. A very symmetric looking construction, a very symmetric looking expression, mathematical expression, that tells you what the time derivative of A is. This mathematical construction, let's generalize it now. Take any two functions of P and Q, A of P and Q, and B of P and Q. Any two.
As your points is constant, how do you get these diverging lines?
Then you define something called the Poisson bracket. That's the symbol for the Poisson bracket. You take A and B, put them inside a bracket, and put a comma between them, and that's the symbol for the Poisson bracket. Its definition is sum over I of all the coordinates, dA by dQ sub I, dB by dP sub I, minus dA by dP sub I, dB by dQ sub I. can see the symmetry of it. It's composed of two terms, one in which A gets differentiated with Q, one in which B gets differentiated with P, and vice versa. That's called the Poisson bracket of A and B. We will see that another formulation of classical mechanics is to write everything in terms of these Poisson brackets. But here we are. Let's rewrite. This tells us that any quantity, the time derivative of any quantity at all, whether it's conserved or not. In fact, what I'm talking about now is not conservation, but the time derivative of any quantity. And that's equal to the Poisson bracket of A with the Hamiltonian. The Poisson bracket of any quantity with the Hamiltonian is its time derivative. That's another formulation of mechanics, closely related to Hamilton's. But if you're interested in whatever it happens to be, if you can express it in terms of positions and momenta, then its time derivative is given by the Poisson bracket with the Hamiltonian. The Hamiltonian is a special object which generates velocities, generates time dependence by taking Poisson brackets. So as I said, this is yet another formulation of quantum mechanics, classical mechanics, where the motion of any quantity is expressed in terms of Poisson bracket with respect to the Hamiltonian. Let's just check it. Let's do one or two examples. If you like, this is a generalization of Hamilton's equations. It includes Hamilton's equations. For example, let's check Q dot. Q dot must be the Poisson bracket of Q with H, according to those equations. Let's see what that says. That says one variable now, one P and one Q. That says dQ by dQ, dH by dt, minus dQ by dP, dH by dQ. I've now just substituted for A, just good old Q. Q dot is the Poisson bracket of Q with H. The Poisson bracket of Q with H is dQ dQ, what's that? 1. All right, so this is just 1. What's dQ by dP? 0. Q and P are independent variables. This goes away. And this just says that Q dot is dH by dP. No, that's Hamilton's equations. What about P dot? P dot is the Poisson bracket of P with H. That's dP by dQ, dH by dP, minus dP by dP, dH by dQ. What's dP by dQ? 0. And dP by dP? I think I just erased the minus sign. 1. So that's the other of Hamilton's equations. So the two Hamilton equations are special cases of a much more general rule that the time derivative of anything is the Poisson bracket of the anything with the Hamiltonian. This gives a new view of Hamiltonians as generating time dependence by the action of Poisson brackets. The action of taking the Poisson bracket for the Hamiltonian tells you how systems change with time. That's yet another representation of classical mechanics. I think that's probably, let's stop for questions and not to go any further at this point.
Is a carbon tax a conservation law?
What's that?
Is a carbon tax a conservation law?
Yeah. Oh, well, since I started talking about conservation laws, now we see that it's a necessary and sufficient condition to have a conservation law that the quantity in question have 0 Poisson bracket with the Hamiltonian. Now, that may seem like an incredibly abstract view of things, and it is, but it's also a very powerful and very general formulation. If you want to know whether something's conserved, you Poisson bracket it with the Hamiltonian, and if it's 0, then it's conserved. If it's not 0, then whatever it is gives you the time derivative. So, try it out for angular momentum, for example. Try to take just a free particle and see that the angular momentum is conserved by taking its Poisson bracket with p squared over 2m and so forth. Let's just take some questions now and stop for the evening, because I think we've probably done enough for tonight. This is very abstract, but it is very powerful. Powerful means that apart from the fact that you can use it to calculate, which you can, more important, actually, we haven't discussed the fact yet that density of points is constant. Not only the structure of classical mechanics, but quantum mechanics reoccurs and reoccurs and reoccurs all over the place. Yeah?
How did Poisson come up with that?
What's that?
How did Poisson come up with that?
I really don't know. I wouldn't be surprised if he came up with it exactly this way, by calculating small changes in things. My guess is he came up with it exactly this way.
Yeah. When did you find the bracket? When did you find the bracket? You're using the chain rule there.
Well, we just found this structure recurring in many contexts. I mean, you know, that's when, now we're going to study more general Poisson brackets, not just with the Hamiltonian, but between any pairs of things. But you know, mathematicians, good mathematicians, and theoretical physicists are people who tend to see patterns. They see the same thing a couple of times, and they say, a pattern. I see a pattern, and he saw the same pattern occurring in a couple of places, and he said, I'm going to call it a key bracket.
What are some other examples where B is not H?
I just did another key.
You mentioned at the end of the lecture that this is near a large body, so it's energy lost.
Yeah.
I don't think we ever really got back to that.
Oh, wait, you're talking about the non-conservation of energy?
Right.
Yeah, good. Okay. All right. I have assumed that both the Lagrangian and the Hamiltonian do not explicitly depend on time. Now, by explicitly depend on time, it means that there's some time dependence above and beyond the fact that the Q's and the P's or the Q's and the Q dots depend on time. Let's go and ask what happens if the Hamiltonian really does depend on time. How can that happen?
Well,
You
it's
said-
dumping in energy, right?
Yeah. Well, let's suppose there's a big lump of matter over here. Our system is over here. We're not going to include this as part of the mathematics of our system, but it exerts forces on here. And it's moving. It moves from here to here in a certain way. That will mean the forces on this system will depend on time. In fact, there will be a term in the energy. Let's just take a single particle. There will be a term in the energy of this particle, u of its position, which also depends on the position of this big lump. But the position of the big lump depends on time. So that means the potential energy depends on x and also explicitly time. It means it depends on time even if the particle doesn't move. It certainly depends on time just because x may depend on time. But that's an implicit dependence on time. There's also an explicit dependence on time corresponding to the fact that the source of the force happens to be moving. All right. If the Hamiltonian depends explicitly on time, let's go back. calculate the time derivative of the energy itself. This was our equation that we had a few minutes ago, and these two things canceled because P dot and Q dot are also derivatives of H. But there's just another term. If H also depends on T, then we have to write that the time derivative of H is dH by dP times P dot plus dH by dQ times Q dot plus the explicit derivative of H with respect to T. In other words, the change in the Hamiltonian, even if P and Q are standing still, if P dot and Q dot are equal to 0. That's what happens if the potential energy, for example, depends explicitly on time. Then this would, of course, be just du by dt. That's what it would be. All right, so in that case, even though these two terms completely cancel each other by virtue of Hamilton's equations, there's another term left over. Just the explicit derivative of H with respect to T. And that's, in general, not 0. It won't be 0 if the Hamiltonian, it says what it says. If the Hamiltonian explicitly depends on time, then that will appear in the equation for the time derivative of the total energy. So that's as simple as that. We can do some examples. It's getting a little bit late. I don't want to do an example now, but let's come back to it. An example of a time-dependent Hamiltonian.
No, just a little definition in the Poisson bracket. Which is there a convention in terms of which order there is? Because there's a minus between the two.
I hope my convention is the same as Poisson's. And I'm not sure it is. See, I always define it this way. A comma B is the A by dQ, the B by dP, minus the A by dP, the B by dQ. And you know, I don't think I've ever looked that up to see if it's right.
But well, my question was, since you said it's general, not just Q's and P's being, you know, these variables, is it A of Q comma P or A of P comma Q? As just a mathematical definition.
A
In other
just
words,
depends
is
on
P
Q.
or Q, which is the first variable, which is the second? He said this is just an abstract definition. You see what I'm saying?
I don't think that means anything. You can write it either way. I mean, we make a convention. Let's make a convention.
Isn't one minus the other?
Hmm?
Couldn't it be the A, the P, the D, the Q?
We could define it by dA by dP, dB by dQ minus the other one, but this is the way it's defined.
That's not my question. Since you said you have a function A of P and Q, okay, does that mean that Q is the second variable? Or you say A of Q is the same as A of Q and P?
Are you taking the derivative of A with respect to the first variable or to the second variable in your capital letter?
Which one is first and which one is second?
You choose.
No. There's no first and second. There's P's and Q's. That's all.
Normally you put Q position first before momentum.
If you like. But remember, they're different.
You're just going to end up with one variation of the Poisson bracket
Tell me.
and then minus of the other.
Right.
If I write that the Hamiltonian is P squared over 2m plus 1 over x plus gm m over x. Will you please tell me which is the first one and which is the second one? It's just two variables.
No, but it will reverse the sign.
You get a reversal of the sign.
No.
No, I said
I'm never going to tell you whether x is the first variable. I don't want to differentiate something in the denominator. Please don't force me to.
I understand what you mean. I understand when you mean momentum and position, that there's only one way of saying it. That's not my question. You said as an abstract mathematician, you said that this Poisson bracket's going to come up in all kinds of places.
Yeah.
So maybe that's not momentum and position, in which case it doesn't matter which is which variable. And I was wondering if there was a definition, that's all, not a convention.
As to the sign of the
This particular structure doesn't come up anywhere that I know of except in mechanics. But some people seem to be under the impression that it's important to describe whether x is the first variable or the second variable. It's not. It's just the x variable, and p is the p variable. When I calculate dh by dp, I don't have to ask whether p comes first and x second, and so forth. Now, you could have defined the Poisson bracket in the opposite way. In fact, you could have defined the Hamiltonian with the opposite sign. All kinds of things we could have done differently. We made some conventions. This is one of the conventions. I don't know what else to say about it. Let me answer your question. Okay, so that's... You're not satisfied.
The only question I had was a pure mathematical one where you didn't know what P was, you didn't know what Q was, it wasn't momentum, it wasn't position, okay?
Right.
In which case, there is a difference of a minus sign. And the only reason I asked that is you said Poisson brackets come up all over the place, and I didn't know that it was always in the nature of position and momentum.
Yeah, I don't know any other place where Poisson brackets come up, except for positions and momentum. What I did say comes up all over the place is Legendre transformations. Legendre transformations do have this habit of coming up all over the place. The equations for Legendre transformations don't have a funny minus sign in them. They read dl by dv is equal to p, dh by dp is equal to v. So in that particular case, there is no
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.